Thank you for coming. Today, I'm going to present a new code injection technique by using binary translation cache file. My name is Ko Nakagawa, and I am a security researcher at FFRI Security. My main research interests vulnerability research and reverse engineering. There is a co-speaker Hiromitsu Oshiba. He is a research director at FFRI Security. His main research interests vulnerability research, threat intelligence, and malware analysis. Its outline of this talk. First, I introduce Windows 10 on ARM. Then I talk about binary translation cache file and its reverse engineering result. Then I talk about new code injection technique and its use cases. Then I conclude this talk and show some GitHub links to POC code and tools. So let's get into it. ARM processors have been used for laptops, not limited to smartphones due to its energy efficient feature. For example, Microsoft launched Surface Pro X last year, which runs Windows 10 on ARM. Other vendors Hewlett-Packard also launched a similar product called HP MBX2, which runs also Windows 10 on ARM. Recently, Apple also announced the Mac transition to ARM-based Apple Silicon. So ARM-based laptops will be becoming very popular. However, there is a barrier to the transition from Intel to ARM for many users. Since these two architectures are entirely different, we cannot use existing software for Intel on ARM-based laptops. But don't worry, Microsoft and Apple provided the solutions for such a problem. Microsoft announced x86 emulation feature for Windows 10 on ARM. This enables execution of x86 application on ARM-based laptops by JIT binary translation. Apple also announced a similar binary translation technology called Rosetta 2, which runs both at install time and runtime. But you might think that, hey, binary translation for every application launch? It seems to be very slow. But again, don't worry. When you look at Microsoft documentation, you can find that service caches these translated blocks of code to reduce the overhead of instruction translation. These translated blocks of code are cached as a file. This file is called XTA cache file. It reduces much of JIT binary translation overhead. So when the translation result is in the XTA cache file, JIT binary translation is not performed. So this caching mechanism improves the performance of x86 emulation. How does emulation work? Before explaining, I introduce three major components of x86 emulation. XTJIT is an emulator DLL loaded by WAL64 layer. Xstack is a compiler that creates or modifies XT cache files. XT cache service is a service program that manages XT cache files. It also creates or modifies XT cache files by running Xstack. From now on, I show some reverse engineering results of x86 emulation and XT cache file. Some results rely on silence research chain block. Here I show a flow of execution of x86 emulation using XT cache file. When the x86 application runs, XTJIT DLL is loaded to the memory, and it notifies to the XT cache service through LPC. Then this XT cache service searches a cache file for the application from this cache file directory. If it finds cache file for the application, then this XT cache file is mapped to the memory with read and execute protection. Then threads of this process transfer the control to the cache file if needed. If the thread encounters a code block that is not in the cache file, it translates some code blocks dynamically and writes the content to the heap region, then transfers the control to the heap region. Where are XT cache files? We can find XT cache files in the system root XT cache directory. As you can see, there are several XT cache files in this directory. Like this, By default setting, full permission is granted only to XA cache service. However, with admin equivalent privilege, we can change the directory's permission to other owner. So after changing the directory's permission, we can read and write XA cache files in this directory. You might notice the distinctive name of XA cache file. Its name is roughly composed of 4 words: name of executable, hash value by file content, hash value by file path, and the number of updates. I'll explain the update feature of XA cache file later, but Xtag updates an XA cache file to add newly translated blocks of code. How does XA cache service search XA cache files? To do this, XA cache makes the string for searching. It first calculates the hash value by file content and file path, then combines these results with the name of executable. The number of updates is specified as a wildcard. By using this string, XA cache service searches the cache files for the application. If it finds multiple cache files, it uses the cache file whose number of updates is largest. Cache files whose number of updates is smaller are not used, and these files are removed later. Next, let's dig into the structure of XA cache file. Here I show the schematic picture of XA cache file. Header holds the offset to the following blocks. BLCK stub contains code for bridging between XA cache and XAG, and the address lookup operation function, and so on. After this, there is translated ARM code. These 2 blocks are repeated for the number of updates. After these blocks, there's address pairs. Address pairs contains the relation between the RVA of the x86 application and the offset of translated ARM code. Finally, there's empty path name of x86 application. Here I show the reverse engineering result of XA cache file header. It contains magic number, which is always XDAC, and file version, and this cache file is updated or not, and the offset to the following blocks, and the module name of x86 application. I don't explain all of these members of this structure here, so for more details, see the appendix of this material. Here I show some example of translated ARM code. You can see that translated ARM code exists without any obfuscation and encryption. So when you disassemble this XA cache file, you can get ARM assembly, translated ARM assembly like this. Next, let's examine this translated ARM code. During emulation, ARM general purpose registers have special meanings, and each RAM register corresponds to each x86 register. This table shows the such relationship between these 2 architectures. By using this table, we can understand this translated ARM code. For example, W29 register correspond to EBP, and W28 register correspond to ESP register. So the meaning of this instruction is store the value of EBP to the stack top, and the stack top is decremented by 4 bytes, which is equivalent to push EBP instruction of x86. I determined this table by reverse engineering the context switching operation of XTAG. As you can see, EDI register corresponds to W20, and the ESI register corresponds to W19, and so on. Next, let me explain the update feature of XA cache file. As I said, Xtag updates XA cache file to add newly translated code. In the process, the previous translation result is copied to the new cache file to reduce the amount of binary translation. but small patches are applied to the previous translation result before copying. So I don't explain the purpose of these small patches. So for more details, see the appendix of this material. Here I show the schematic picture of XA cache file update. Before update, there are VLCK stub and translated code in the XA cache file. After updating, these two blocks are copied to the new cache file with small patches and extract as newly translated code to the end of previous translation result, like this. But this update process can be prevented by modifying cache file header. Extract uses pointer to extract linked list head member for getting the position to be patched. So assigning an invite value to this member crashes extract and prevents the update of XA cache file. I note that this change does not affect the cache file loading and execution of x86 application by XAJIT. So although invite value is assigned to this member, XAJIT can load this XA cache file. Here, let's quickly recap about the XA cache file. It contains translated ARM code without any obfuscation and encryption. During emulation, this cache file is directly mapped to the memory with read and execute protection. It is also updated during or after emulation, but this update process can be prevented by modifying cache file header. Although specific cache file header member is modified, XAJIT can load this cache file. Here, let's reconsider the raw translated code exists in the XA cache file. If we modify code in the XA cache file, what will happen? Unfortunately, XA cache service does not check the integrity of XA cache file before loading. So if we modify code in the XA cache file and the application runs, this modified cache file is mapped to the memory with read and execute protection, and through user emulsion process, we can execute code in the modified cache file. And to make matters worse, there are no limitations for the embeddable content of XA cache file, such as size or encoding, so we can embed shellcode in the XA cache file and write through emulation. We are calling this code injection technique as XTA cache hijacking. I note that there are some limitations to callable APIs for shellcode. Some native APIs of DLLs in System32 are not callable, such as GDI or WinSock. However, APIs of WAL64 layers are of course callable. Next, let me explain the features of XA cache hijacking. There are three features of XA cache hijacking: difficulty detecting, difficulty root cause analysis, and persistence. First, this technique is difficult to detect because access to the target process are not needed, such as actualization of target process handle. Moreover, code injection is performed without any suspicious API calls. So when we modify code in the XA cache file and application runs, modified cache file is mapped to the memory, and the code in the modified cache file is executed automatically. And this technique is difficult to analyze its root cause, so we cannot determine the root cause by simply examining the x86 application. Here, let's consider the simple example. Let's consider the x86 malicious. Let's consider the case that x86 mal shows the malicious activities, and these activities are saved as a log file. An incident response team analyzes the log and finds this executable shows the suspicious activities. However, he cannot find any indicators of these by simply inspecting this executable. Without examining the XA cache file, he cannot find its root cause. Therefore, As an effective countermeasure to exit cache hijacking, monitoring cache file activities is essential. And this technique is persisted as an exit cache file. So even after OS restart, same code is injected to the target process. As I said, updates of exit cache file can be prevented by modifying cache file header, so we can achieve persistence by preventing cache file update. When does an attacker use this technique? To discuss this, let's see the positions in the multi-attack matrix of this technique. This technique can be used to achieve three tactics: persistence, defense evasion, credential access. First, this technique can be used as a persistence method, so we can hide malicious shellcode in the exit cache file. Next, this technique can be used to mask malicious code, so we can run malicious code as a legitimate process to bypass a broker or antivirus products. And this technique can be used as a credential access method, so we can inject API hooking code in exit cache files of DLLs that are used in a browser. Through this code injection, we can steal credentials or modify web pages. I mean, this technique can be used as a part of MITB attack. But you might think that, hey, exit cache hijacking seems to be similar to other conventional code injection techniques. What makes exit cache hijacking so special? Why is it so interesting? Hyometsu will answer this question. Now I'll hand it over to Hyometsu.
Thank you, Cole. Okay, as he explained, it's a new code injection technique. It targets a new platform, and it has three features organized in might attack. Good, but that's all? The technique was privileged? Yes, we think so that. Please remind that it is realized by modifying cache of translation result. Of course, there are M64 instructions, not x86, although we are targeting x86 processes. In other words, we can change the behavior of x86 processes without any modification to x86 instructions. Funny. What's happening? x86 instructions are loaded on memory, but the CPU cannot execute them directly. And x86 instructions are only referenced when translating them into M64. And they are not referenced if already cache exists. So the instructions in the cache will be executed even if the behavior of the cache and the original code are actually different. So this technique has a side effect. As a result, execution of payloads is invisible to x86 layer. This caused by two things. First, there are no changes for x86 instructions on memory, as we already explained. Second, the execution state on M64 layer is invisible to x86 layer. So even if you're following the execution with the backwards step by step, you can see just only execution of unmodified x86 instructions. So the execution of a payload is invisible. We call that invisible execution. Here's an example to illustrate this. This is a program actually do nothing. It has only jump code, and destination is instructions with no meaning, but it will show letters in console. Check in the cache. Interesting, but is it useful? Okay, let's talk about use cases. One of them is API hooks. It is very useful technique for inspection, changing behaviors, and so on. But it is easy to detect because it is invasive. It always leaves some traces. For example, code hook is commonly used technique. It rewrites instructions at the beginning of the function, and so we can detect this, check the instructions at the beginning of the function. But we can avoid the detection like this or tracing with our method invisible execution. CHPD allows a good hook point to do this. They are bridge DLLs between x86 and M64. They are used in x86 processes on Windows 10 ARM. They exist for some DLLs frequently used, like kernel 32 and etc. Most of hook point is covered by CHP DLLs. And this is most important. They have x86 stub calls for each API. Of course, cache is generated for these APIs. So we can apply the technique to these DLLs and use for hook point. Conclusion. We provided technical details about new code injection technique for Windows 10 ARM. It exploits the cache in XDG8, and it has 3 features organized in MITRE tag. And it has a unique side effect because it exploits this target. What have to do based on this? For developers or similar system, you may have to do similar to XDG8, and it will be interesting target for attackers. So please ensure the integrity of the cache. This technique requires privilege, but still worth think. For everyone, be aware of the threat. It will be difficult to find using this technique on first seeing, so please be aware. PLC code and summarized tools are available here. One more thing, we can use the cache for another purpose. The cache generated for only the path actually went through. So we can find out the path actually executed from the existence of the cache. There are 2 use cases. First, dynamic but non-invasive coverage measurement. It may be good for fuzzing. Second, it can be useful for analysis during instant response. For example, if you want to know about which command did route executed in your environment without communication logs, it can help you. Therefore, this will also be available. Thank you for listening.